It defies common sense. A crane platform floating on the unpredictable surface of the ocean should be fundamentally less stable than one in contact with solid ground. Yet, the largest floating cranes in the world can lift loads that don't just rival their land-based counterparts, they completely dwarf them. We're talking about lifting entire buildings, massive bridge sections, and multi-thousand-ton oil rig modules in a single go. How can a machine achieve its greatest strength from a foundation of water? The answer is an incredible feat of engineering that turns a perceived weakness into the ultimate advantage. This is Hard Hat Industries, where heavy machinery shapes the world. For any heavy lift professional, the biggest challenge isn't always the load itself. It's the ground beneath your feet. Every land-based crane, no matter how powerful, is in a constant battle with gravity and ground pressure. At the top of the conventional crawler crane class, you have machines like the Liebherr LR13000. It's a true titan, capable of lifting an immense 3,300 US tons. But to achieve this, it concentrates its entire weight onto its tracks, creating enormous ground pressure that requires extensive and costly foundation work. To solve this problem, engineers developed the next evolution in land-based lifting, the ring crane. Instead of crawler tracks, these machines sit on a massive steel ring, spreading the load over a far greater area. This design was a game changer. It led to the creation of the Saren's SGC250. With a ring diameter of about 159 feet, this crane can lift a staggering 5,500 US tons, all while boasting a ground pressure of less than 36 pounds per square inch, similar to a car tire's inflation pressure. It was, for a time, the largest land crane in the world. But the ambition for bigger lifts didn't stop. The current king of the land is the Mammoet SK6000. Also a ring crane, it pushes the limits of engineering even further, capable of hoisting an unprecedented 6,600 US tons. These machines are the absolute pinnacle of what is possible on solid ground. These machines represent the peak of engineering, perfectly tailored for the logistics of land-based construction. But the open ocean operates by a completely different set of rules. Out there, the primary challenge is to minimize complex assembly at sea, which demands lifting single modules on a scale that land-based projects don't require. This logistical necessity drove the evolution of a separate class of machine with, by comparison, over 3 times the lifting capacity. The real engineering paradox is how engineers turn the unstable sea into a foundation strong enough to solve a problem that land cranes were never designed to face. At first glance, putting the world's heaviest crane on a floating barge seems like a recipe for disaster. Water is fluid, unstable, and constantly in motion. But the engineers behind the largest floating cranes discovered a way to transform this instability into the most robust lifting platform ever conceived. The secret isn't in the crane itself, but in the vessel it's mounted on, and its mastery of a principle first understood by an ancient Greek mathematician: buoyancy. A floating crane vessel, or SSCV for semi-submersible crane vessel, doesn't just carry a crane. The entire ship is the crane system. Its first advantage is its enormous footprint. A vessel like the Saipem 7000 is approximately 650 feet long and 285 feet wide. It spreads its massive weight over an area of thousands of square feet, making ground pressure a complete non-issue. But the real genius lies in its ballast system. Inside the hull of an SSCV are a series of massive tanks, connected by a network of pipes and highly powerful pumps. These pumps can move thousands of tons of seawater between tanks within a short period. This water is the crane's counterweight, a dynamic, fluid, and perfectly controllable force. This isn't just a trickle of water. We're talking about a coordinated system that can move over 20,000 tons of seawater, the equivalent of 8 Olympic-sized swimming pools, from one side of the hull to the other in a short period. This rapid transfer is what allows the vessel to react in real time, creating an active, intelligent foundation that perfectly counters the immense forces of the lift. It's a precisely choreographed dance between gravity and buoyancy, performed on a scale that is difficult to comprehend. Here's how the paradox works. When a land crane lifts its load, it relies on a fixed, static counterweight. In contrast, when a floating crane prepares to lift a 10,000-ton offshore module, it actively pumps tens of thousands of tons of ballast water into the tanks on the opposite side of the vessel. As the crane takes the load and the vessel begins to list or heel to one side, the ballast system responds rapidly, shifting that water to counteract the force and keep the vessel perfectly level. This system leverages Archimedes' Principle on a colossal scale. As the vessel takes on more ballast water, it gets heavier and sinks slightly lower in the water. By sinking lower, it displaces more water, and the buoyant force pushing up on the hull increases. In essence, the heavier the load on the hook, the more ballast it takes on, and the more stable its foundation becomes. It is a system that grows stronger as the demands upon it increase. This is something no land-based foundation could ever do. This stability is further enhanced by the semi-submersible design of the most advanced vessels. It's an ingenious concept. By intentionally flooding its lower pontoon holes, the crane can sink its operational draft deeper into the ocean. This lowers the vessel's center of gravity dramatically, making it exceptionally stable against the forces of wind and waves. The majority of the vessel's structure sits below the turbulent surface, creating a steady platform that can operate safely in the unforgiving conditions of the open ocean. And this capability has completely reshaped our world. It's no longer just about lifting heavy things, it's about enabling progress on a global scale. The entire offshore oil, gas, and wind industry, trillion-dollar sectors that power our modern world, would be impossible without this technology. Building massive bridges across deep shipping channels, salvaging sunken vessels from the ocean floor, these are tasks that can only be accomplished by turning water from an obstacle into an asset. The principles of buoyancy and ballast have given rise to a fleet of machines that are difficult to comprehend. These aren't just tools, they are floating mega projects in their own right, with capabilities that redefine what is possible in construction. The undisputed king of this fleet is the SSCV Sleipnir, operated by the Dutch firm Heerema Marine Contractors. Built at a cost of $1.5 billion, the Sleipnir is a testament to the power of this technology. It is a semi-submersible vessel, meaning it can partially flood its lower hulls to sink deeper into the water, providing extreme stability even in rough seas. It's powered by 8 engines, generating approximately 96,000 horsepower. But its fame comes from its 2 main cranes. Developed by Houseman, these cranes are a marvel. Each one can lift 11,000 US tons. When working in tandem, they can lift a combined total of up to 22,000 US tons under optimal conditions. To put that in perspective, that is the equivalent of lifting 2 Eiffel Towers at once. In 2019, the Sleipnir set a world record by lifting a 16,865 US ton topside module for an oil platform in a single piece. A lift of this magnitude saves months of complex, dangerous, and expensive offshore assembly work. This isn't just about brute force, it's about surgical precision on a staggering scale. For an operation like this, the vessel's dynamic positioning system must hold it steady within a few feet, battling ocean currents while the crane operators, guided by an array of sensors and computers, delicately lower the multi-thousand-ton module into place. The final margin of error is often measured in inches. It's this combination of immense power and pinpoint control that truly makes these machines the undisputed kings of marine construction. Another giant is the Saipem 7000. For decades, it was the largest crane vessel in the world, with a combined lifting capacity of 15,400 US tons. It has been a workhorse of the industry, responsible for installing over 160 offshore platforms and contributing to deep-water pipeline projects. These vessels are the quiet enablers of our modern infrastructure. They operate far from public view, in the harsh environments of the North Sea or the Gulf of Mexico, performing lifts that were once considered physically impossible. They are a stark reminder that in the world of heavy construction, the most brilliant solutions are often found by looking at a problem from a completely different angle. So, the paradox of the floating crane is solved. It's not that water is stronger than land, it's that engineers learned how to master the principles of buoyancy and ballast to create a lifting platform that is not only bigger, but smarter. While land cranes are in a constant fight against the ground, these titans of the sea have made a partner of the water. That 10,000-ton lift, impossible on land, becomes just another day at the office, thanks to some of the most impressive engineering on the planet. Thanks for watching Hard Hat Industries, your source for serious machines doing real work. If you like this, hit like, subscribe, and turn on notifications so you don't miss what's next. Until then, keep your head down and your gear running.